Let's talk about the solutions for the 2.9 activities. You're given this matrix A, its reduced echelon form U, and another matrix V. The first question is about the rank of A. So the rank of A, by definition, is the dimension of the column space of A. And so if we look at the echelon form, we see the pivot positions. They fall in columns 1, 2, and 3, which tells us that we can take, for a basis of A, the first 3 columns of A, the basis for the column space. Since we can form a basis for the column space of A using 3 vectors, that means the dimension is 3. Now this is exactly equal to the number of pivots of A, right? Because we just needed to count, or just needed to see where the pivots are to form a basis for the column space of A. And this happens in general. For all matrices A, the rank of the matrix is equal to the dimension of the column space, which is equal to the number of pivots. In the next problem, you're asked to use the rank theorem, or the Rank-Nullity theorem, to compute the dimension of the null space of A. So the rank theorem says that the rank of the matrix plus the dimension of the null space is equal to the number of columns of the matrix. And we've just computed the rank was 3, the dimension of the null space is what's unknown, and this is supposed to equal the number of columns of A, which is 5. So we can solve for the unknown and see that the dimension of the null space of A is 5 minus 3, which is 2. Next, we're asked to consider the basis B, which is made up of the first 3 columns of the matrix A. And we're asked to show or explain how we can tell that that's a basis. Right? So computationally, I just said that when you compute the echelon form of a matrix to see where the pivot positions are, they tell you which of the columns of the original matrix to take to form a basis for the column space. And what I want now is just an explanation of how or why that's true. Right? So we have these pivot positions in columns 1, 2, and 3. And any linear relationship satisfied by the columns of U have to also be satisfied by the columns of A, and vice versa. Right? And the reason for this is the null space of A and the null space of U are exactly the same space. So any relationship satisfied by the columns of one matrix is going to be satisfied by the columns of the other. Since U1, U2, U3, so the first 3 columns of U is a basis for the column space of U by inspection, we see that A1, A2, A3 has to be a basis for the column space of A. Next, let's try to find a vector B whose B coordinate vector is 3, 1, 0. Right, so the basis capital B, that's the A1, A2, A3, the first 3 columns of A. So, if its coordinate vector is 3, 1, 0, I need 3 times the first column, plus 1 times the second column, plus 0 times the third column. And that'll be my vector B. And so I can just compute. It's 3 times 1, 5, 4, 3, plus 2, 1, 6, 4. And I get the vector 5, 16, 18, 13. All right, that's the vector whose coordinate vector is 3, 1, 0. Next, we're asked to use the echelon form U to find A4 in B coordinates, right, the coordinate vector for the 4th column of A, and also the coordinate vector for the 5th column of A. So let's look at A4 first. That's the 4th column of this matrix A, and we want to find its coordinate vector. Well, if we look in the 4th column of U, we see that the 4th column of U is exactly 0 times the first column, plus 2 times the second, plus 0 times the third. So in coordinate B, that A4 is going to be 0 times A1 plus 2 times a2 plus 0 times a3. And so the coordinate vector for a4 is 0, 2, 0. We can do a similar computation for a5, the fifth column of A. We're going to look at the fifth column of U and see that it's 0 times the first column of U plus 1 times the second column of U plus minus 1 times the third column of U. So that tells us that a5 in B coordinates is 0, 1, minus 1. Now let's look at the set C, which is made up of the columns of the vector of the matrix V. And without computing, I want to know what is A times V1 and A times V2, right? Knowing that U times V1 is the 0 vector and U times V2 is the 0 vector. So notice that V1 and V2 are in the null space of U, since U times V1 is 0 and U times V2 is 0. But the null space of U is exactly equal to the null space of A. So that means that V1 and V2 are in the null space of A, which tell us that A times V1 is equal to the 0 vector, and A times V2 is also the 0 vector. All right, so now let's keep considering this set C, which is V1, V2. How can you tell that C is linearly independent? Well, if you have a set with two vectors in it, and those vectors are non-zero, as long as they're not multiples of each other, the set is going to be linearly independent, right? And so you can look, say, in this fourth entry and see that they're not multiples of each other, and so the set is linearly independent. Next, let's try to use the basis theorem to explain how we can see that this set C is a basis for the null space of A. Well, earlier we saw that by the Rank-Nullity theorem, the dimension of the null space is 2. And so the basis theorem says if we can find a collection with two vectors in it that are independent, it's automatically a basis, or if it generates, it's automatically a basis. And in this case, we found a set with two vectors in it that were linearly independent. Right, so any linearly independent subset of the null space of A with exactly two elements is going to be a basis. That's the basis theorem. And so that tells us that this set C is a basis for the null space of A. And finally, I want to consider the discussion question. So Alice says the null space of A is R2, the column space of A is R3, A has 5 columns, and that's compatible with the Rank-Nullity theorem because R2 plus R3 is R5, right? And so there's various ways in which Alice is mistaken. I think she understands some of what's going on, but she's just saying it incorrectly. And so let's go through this and correct her statements. So first off, the null space is not R2, right? The null space of the matrix A is the subspace of R5, and it's two-dimensional. I think she's confusing with the 2. So the null space is two-dimensional. The next mistake is with the column space of A. The column space of A is not R3, but it is three-dimensional, right? It's a three-dimensional subspace of R4. A has 5 columns. That's correct. And now the rank theorem, or the Rank-Nullity theorem, it doesn't say that the sum of the spaces is the other space. It's talking about dimensions. And so it's saying that the dimension of the null space of A, which in this case is 2, plus the dimension of the column space of A, which in this case is 3, is equal to the number of columns of the matrix, which in this case is 5. And that's the statement, or that's showing compatibility with the Rank-Nullity theorem in this example.